Fantastic. Thanks so much, Dan. And we're actually starting to make up some time, so thank you. Our next speaker is Guillermo Cabrera-Vives. So he's an associate professor at the Universidad de Concepción in Chile. He's the principal investigator for ALERCE, which I'm going to let him tell you all about, but it's a very exciting project. And we're really getting to the point where we need to figure out how to go from pixels, from these alerts, to actually finding anomalies. And Guillermo is going to give us a lot more of those details. So thank you very much.
Thank you. Thank you, Michelle, for the introduction. So, there you go. So imagine you're an astronomer in the future, and what you want to do is you're going to wake up in the morning, you're going to grab a cup of coffee or tea, depending on where in the world you are, and you're going to open your laptop and start interacting with the system, right? And the system is going to tell you, last night we observed through this telescope and that other telescope this potentially important astronomical source, right? So for example, we found a couple hundreds or thousands of supernovae, exploding stars, and we found another couple of thousands of variable stars and AGNs and different types of sources. But I also found something last night that you may be interested in, and this is an anomaly. This is something that I don't know exactly what it is. I got data from this particular telescope, this particular database, and I think that this is an anomaly. So the system tells you this, and then it tells you, you know what? You have follow-up time for tonight. Do you want to follow it up? And you check all the data and say, sure, that's what I want to do. Just do it, right? This is what we're aiming at. So some of the tools I just described already exist. Some of them, they don't, okay? And today I'm going to talk about ALERCE. ALERCE is one of the brokers for the LSST, one of the official brokers for the LSST, which you all heard a bit about it. And we're aiming at building this during the next couple of years. So first, I want to talk about alert streams. So most likely you heard about the light, I know you heard about the light curves and all this, but I want to tell you how these are created. So we have something, a telescope, like the LSST, which has these wide field images, right? So what they do is that they have what's called a template image, and the template image is like a historical image of the sky. And then tonight, we observe and we get what's called the science image, okay? And what we do is that the LSST, well, there's a huge process around this, but it aligns the images with sophisticated algorithms, and then it subtracts them, right? So if something new appears in the sky, it would look something like this, right? So like a point, okay? And so when the LSST finds something like this, it's gonna emit an alert, okay? So if you think about it, during one night, you can have one alert at a position in the sky, and then 2 or 3 nights after that, you may have another alert, and then 2 or 3 nights in the future, you have another one, and so on and so forth. And then you start creating a set of image stamps. This is what they're called, image stamps, okay? And then you can get the photometry, the flux, the brightness of each of these sources, and start putting them in time. So this plot shows the brightness of the source in time. And then for the first night, you have that. For the second night, you have that, and so on and so forth. And this is what it's called a light curve, all right? So we have image stamps, we have light curves, and in principle, they look something like this. This is a real light curve from CDF, okay? And this is a particular supernova. So if you notice, on this plot, I'm only showing alerts, but we don't only have alerts. We can also build a light curve for all sources in the sky. And we can also, and this is what's called the data releases. So you'll have the light curve for all the sources in the sky, or at least the ones that vary. And the other thing that you can do is, if you get an alert tonight, then, there you go. So then, if you get an alert tonight, then you can go back to the images in the past and get the fluxes that were on that position of the sky in the past, okay? So that's what we call force photometry. So we already have 3 types of light curves, right? Alerts, data releases, and force photometry. So Alerce is currently working on CDF data. So we're connected to the CDF data stream, and every night we process CDF. And we're getting around 1 terabyte of data per night, and it's around 1 billion of objects in total, but we're getting around 100,000 to 1 million alerts per night, depending on the night and depending on a lot of things. When the LSST starts operating, this will be 1 or 2 orders of magnitude bigger in data size, in number of alerts. We all talked about this, but 10 million alerts per night, so that's a lot of things. And we need to classify all that and get all the important stuff out of that alert stream. So that's when the brokers come in. So what are the brokers? So in the future, maybe not that far in the future, we have the survey telescopes, right? And the survey telescopes will communicate their alert stream, all the alerts they found every night, to the community brokers. The community brokers, so there are 7 of them that are officially brokers for the LSST, and the community brokers will connect to the downstream brokers, so these are specified brokers for specific scientific cases, but also directly to follow-up resources or to the users community. Okay? And what most likely is going to happen is that after getting all this data processed, we will want to go back and get more data for particular sources. The brokers have different products and services that they're developing. I'm going to talk particularly about 3 of them right now. So it's about classification, calculating features, and of course outliers and anomalies. So just to let you know, there are 7 official brokers for the Vera-Rubin Observatory. There are 3 in the US, 3 in Europe, and 1 in Chile. Alerce is the one that's built in Chile, and it's one that is based on a lot of machine learning models behind the scenes. So now I want to talk about the models. What type of models we have? First, we have what we call the stamp-based classifier. This is like a really fast classifier. So when we get an alert, we get the stamp images, and we classify them really quick, okay? And it's basically a convolutional neural network behind the scenes. And what we do is that we built what's called the supernova hunter. So every morning, you can connect to the supernova hunter, and you can see all the transients that were classified by Alerce last night. Okay, so that's one of the use cases that we already have running. So thanks to the supernova hunter, we've been submitting detections of supernovae to TNS every night, or every morning actually, because the astronomers wake up in the morning and they make sure that everything is correct. And we are the 3rd group around the world that posts more supernova in the sky after, to TNS, after pan-stars and CDF. We also have our light curve classifier. So the model I showed before only classifies into 5 classes. One of them is supernova, the other one is asteroids, AGNs, and other 2 classes. But we also have like a classifier that works on a more detailed taxonomy, and that's what we call the light curve classifier. So how it works, it's basically we have light curves, as I explained before, and we calculate a whole bunch of features from the light curves. And we calculate around 185 features from the light curve. And we have 2 models. One of them is a balanced hierarchical random forest. This is like a standard classical machine learning model. But we also have a time series plus tabular transformer. This is a more sophisticated deep learning model. And those 2 models are already producing classifications. And well, the balanced hierarchical random forest code name is Handsome Squidward. This was an idea from the engineer team. I don't know why they choose that. And the second one, the paper, is called ATAT, but the engineering team called it Mbappé. Don't ask me, ask them why they did this. All right, that's their code name. And we also have an anomaly detector. So how does this work? It's very similar to what Dan exposed before. So basically, we have the data. We put all the data into a neural network that finds a latent space where the different classes are clustered together. And then when we find, when we look for an anomaly, we see how far away from those clusters these objects are. Okay? And through an anomaly detector on the first run, which was working on alert data, what we did is we found a lot of TDEs and microlensing events. Okay, so those were anomalies at that time, but they are not anomalies anymore, because now they are part of our taxonomy. And on the new model that should be put into production this week, those are going to be part of the taxonomy. But we also find stuff that is weird, that we don't know what it is. So the brokers are built to enable new discoveries, all right? This is super important for us. We need the people to use it. We need science to come out of them. Right now, Alerce, there are around 130 refereed papers that use Alerce. There is around 180 papers in total, adding up those that haven't been refereed. That was up to the last time we counted, which I think it was like 1 or 2 months ago. And I want to point at one particular paper that I think is super interesting. And this was led by Paula Sanchez-Saez. And what happened is that she found this particular galaxy that for 2 decades showed no optical variation. And suddenly, on December 2019, Alerce classified it as an AGN. Okay, so something happened there, right? So it was not varying, and suddenly it started varying. Okay? So what they did, they started looking at archival data, and they also did perform follow-up observations of this particular object. And what they found is that there is something weird, of course, because something changed. And the hypothesis they had is that this could be a newborn AGN, or it could be an exotic TDE or something different, okay? So this is the kind of science that I expect to be happening during the next couple of years. You find something weird, something that was not discovered before, and then you say, what can I do about it? Let's go and look for more data on the archives, right? Let's go and do follow-up observations on this. We have also released all the features that we calculated up to May 3rd of 2024, so you can all go and get them. There are around 174 features, and we have used this to look into the feature space for stuff, right? You can go and download it. It's a Parquet file. And what we did, well, we started with one of these, right? So it's a microlensing event. And we said this was one that was discovered by our anomaly detector. And then we found on the feature space a lot of these microlensing events, all right? And that way, what you can do is you can grab all this and put them back into your training set and build models. This is another thing that was curious that we found. We don't know exactly what it is, but we found a bunch of them. A hypothesis is that it's a supernova with circumstellar interaction. So, user stories. This is what computer engineers usually like. Any computer engineer in the room? Can you raise your hand? None? Okay, one. All right, so first, quasi-real-time supernova detection. So CDF is feeding data into Alerce, all right? And you have a human that goes and interacts with the system and asks, what supernova were detected last night, all right? And Alerce responds to that, and then the humans say, okay, I shall report them to TSN, all right? So then you go through Alerce and into the database of TSN, and you submit a new set of supernova, all right? This already exists. This is the supernova hunter I showed before. Another option. So I am the human, and then I want to find a particular class of objects. Okay, so I want to find AGNs. Then I go to Alerce, and Alerce gives them back to me, and then I find something that's interesting, and I say, oh, this one's interesting, then I will go into the data and try, into the archive data, and try to get more data out of it. Or I can perform follow-up observations, okay? And this already exists thanks to handsome Squidward and Mbappé, right? Another one, so historical anomaly detection. I'm the user and I say, what anomalous sources are in the database of Alerce? Okay, so I can interact with Alerce and I say, oh, this one's interesting, so then I can go to archival data or for follow-up to perform follow-up observations, and that already exists thanks to the models we already deployed. So that's fine. Now I'm gonna talk about similarity search. So what sources are similar to this, all right? And I have a whole bunch of sources, and I want to find similar sources to this. I go to Alerce, to the database of Alerce, and then I grab the data, and I can perform follow-up again or go to archival data. That also exists because the feature data set is public. Great. Okay, so now we're going a bit more into the future. So we're gonna think about multi-survey, okay? Quasi-real-time anomaly detection. So in this scenario, what we have is Alerce being fed by multiple surveys. Okay, so as you can see here, we're thinking about optical surveys, but you can also have gravitational waves or whatever type of survey you can find around, right? And then the user comes, and now Alerce tells the user, last night I found this rare object. You may want to check it out, okay? And then the user says, whoa, many thanks. And now I go to the archival data, I perform follow-up observations, and I'm super happy, and I find something weird, okay? Let's say now, we're in the future, a bit further into the future, and Alerce says, last night I found this rare object. Data says this is interesting because, right? And it gives you an explanation on why that is interesting. And usually, in order for that to happen, you will need Alerce to have models that are fed by multi-surveys, but also that are fed through archival data. And now we're talking about multi-model models inside Alerce. Before we were also talking about that, but that's fine. And then I say, really? Many thanks. And I go and perform follow-up observations. And now this is like the far into the future. We say, we want to do semi-automatic follow-up. So Alerce says, last night I found this rare object that we need to follow up immediately. Given that you have allocated time, should I run the follow-up campaign? And you say, let me check first before running anything. And then you say, okay, go for it. And then Alerce performs the follow-up observation. Or maybe a tool, maybe not Alerce, because most likely that's going to have to be connected to the TOMS. So to summarize, what we need is the systems that have to be built and that have to be connected within each other. In particular, we're one of the brokers. There are other brokers, and we're exploring a diversity of use cases. And we need all the brokers to prepare for the LSST, but also to be interoperable with all the data systems that we have. Before leaving, I just wanted to point out that, oh, that slide is not here. Okay, it's not here, but I'm going to tell you about it. So in December, we're holding the Astroinformatics Conference in Puerto Natales. It's one of the most beautiful places in the world, according to me. It's really amazing, and all of you are really invited to come. We have a very limited number of places because the place is very small, but it's really, really nice. So thank you.